In this video, we're going to continue our discussion of top-down parsing algorithms with another strategy called predictive parsing. So predictive parsing is a lot like recursive descent. It's still a top-down parser, but the parser is able to predict which production to use, and it's never wrong. The parser is always able to guess correctly which production will lead to a successful parse, if any production will lead to a successful parse. And it does this in two ways. First of all, it looks at the next few tokens, so it uses look ahead to try to figure out which production should be used, so based on what's coming up in the input stream. But also it restricts the grammars. So this only works for a restricted form of grammars. And the advantage is that there's no backtracking involved. And so the parser is completely deterministic. It will never try alternatives. Now, predictive parsers accept what are called the LLK grammars. And this is a really cryptic name, and so let me explain it. The first L stands for left to right scan. So that means we're starting at the left end of the input and reading left to right. And in fact, that's what we always do. So all the techniques that we look at will have an L in the first position. The second L stands for a leftmost derivation. So we are constructing a leftmost derivation. That means we're always working on the leftmost non-terminal in the parse tree. And K here stands for K tokens of look ahead. And in practice, while the theory is developed for arbitrary K, in practice K is always equal to 1. And so in fact, we'll only discuss the case K equals to 1 in these videos. To review, in recursive descent parsing at each step, there may be many choices of production to use, and so we need to use backtracking to undo bad choices. In an LL1 parser, at every step, there's only going to be one choice of productions, of possible production to use. And what does that mean? Well, it means that if I have an input string, if I have a configuration of the parser where I have some terminal symbols omega and a non-terminal A, possibly now followed by some other stuff. There could be terminals and non-terminals, but again, A here is the leftmost non-terminal. And the next input is a token T. Well, then there is exactly one production. A goes to alpha on input T. Okay, there's only one possible production that we can use. And any other production is guaranteed to be incorrect. Now, it can be that even A goes to alpha won't succeed. It could be that we will be in a situation where there's no production we could use. But in an LL1 parser, there will always be at most one that we could use. So in this case, we would choose to rewrite the string to omega alpha beta. Let's take a look at our favorite grammar, the one we've been using for the last couple of videos. We can see an issue here with using this grammar for a predictive parser. Take a look at the first two productions for T. They both begin with int. And so if I tell you that the next terminal in the input stream as we're parsing along is an integer, that doesn't really help you in trying to distinguish between these two productions and deciding which one to use. So in fact, with only one token of look ahead, I can't choose between these two productions. And that isn't the only problem, actually. So we have the problem with T, but the same problem exists with E. We can see that here, both productions for E begin with the non-terminal T. And it isn't really clear what we're to make of that, because T, again, is a non-terminal, not a terminal. So how would we even do the prediction? But the fact that they begin with the same thing suggests that it's not going to be easy for us to predict which production to use based on only a single token of look ahead. So what we need to do here is we need to change the grammar. This grammar is actually unacceptable for predictive parsing, or at least for LL1 parsing. And we need to do something that's called left factoring the grammar. So the idea behind left factoring is to eliminate the common prefixes of multiple productions for one non-terminal. So that's a mouthful. Let's do an example. Let's begin with the productions for E. And we can see again that both productions for E begin with the same prefix. What we're going to do is just factor out that common prefix into a single production. So we're going to have one production where E goes to T, and then we're going to have multiple suffixes. So let's introduce a new non-terminal X that will handle the rest. So here we have E goes to TX, so it says that everything that E produces begins with T, and that's consistent with these two productions. And now we have to write another production for X that handles the rest. And what would that be? Well, one possibility is that we're in this production, we need to have a plus E, and then in this production there's nothing. So that's easy to handle. We write one possibility for X is that it goes to plus E, and the other possibility is that it goes to epsilon. And now you can see the general idea. We factor out the common prefix. We have one production that deals with the prefix, and then we write, and we introduce a new non-terminal for the different suffixes, and then we just have multiple productions, one for each possible suffix. And you can see what this is going to do. This is effectively going to delay the decision about which production we're using. So instead of having to decide immediately which production we're going to use for E, here in this grammar, we wait until we've already seen the T, whatever is derived from the T, and then we have to decide whether the rest of the production is a plus E or the empty string. Let's do the other set of productions. So we have T goes to, and now the common prefix is int that we want to eliminate. So we're going to have just one production that begins with int, and then we'll have a new non-terminal to stand for the various possible suffixes. And now here we also have another production that doesn't have anything to do with int, and so we just leave that one alone. That production just stays here. Because it already begins with something different, we won't have any trouble predicting between these two possible productions. And now we have to write the productions for Y. And again, we just take the suffixes of the productions that we left factored and write them down as alternatives. So one is empty and the other one is times T. So we wind up with times T or epsilon. So here's the left factored grammar now typed out neatly. And we use this grammar to construct a parsing table. And let's not worry right now about how we got this table. I'm not going to give the algorithm right now. But let's just say that we got it somehow. And what I'm going to explain is how we use the table. So one dimension of the table is the current leftmost non-terminal in the parse tree. So that's on the rows. And then the columns represent the next input token. So the next token in the input stream. And then the entry is the right-hand side of the production to use. So which production that we should use at that point in the parse. That's the production that's predicted. So let's do an example. So let's look at the eInt entry. So this entry right here. And what this says is that when the current non-terminal is E, meaning the leftmost non-terminal in the parse tree, and the next input is int, the thing that we see coming up in the input is an integer, then we should use the production E goes to Tx. So we should expand E with the children Tx. Let's do another example. So when the current non-terminal is Y, and the current token, the current input is plus, then we should use the production Y goes to epsilon. Okay, what that says is, it's a little bit different situation than the previous one. It says, look, when you see a plus in the input and your current leftmost non-terminal is Y, the only way this parse is going to succeed is if the Y doesn't produce anything. You need to get rid of the Y and move on to another non-terminal, whichever one is leftmost after you get rid of the Y, if you want to have any hope of parsing this particular string. And finally, notice that a lot of the entries are blank, and those are error entries. So let's take a look at the E star entry. That says that if the leftmost non-terminal is E, and the next input token is a times symbol, a star, well, then there is no move that you can make. There is no production you can use for E that's going to successfully parse that input, and this is the point at which you would raise a parsing error. In the rest of this video, I'm going to give the algorithm for parsing using a parsing table, and then in future videos, we'll explain how to construct a parsing table. So the method for parsing using a parsing table is similar to recursive descent, except that for the leftmost non-terminal S in the tree, we look at the next input token A. And then, as we just illustrated with the examples, we look up in the table the production to use at the entry S comma A. And instead of using recursive functions to trace out the parse tree, we're going to have a stack of records that can record the frontier. And so at any point in the parse tree, we will have some non-terminals that have yet to be expanded. Those are always at the frontier, at the current leaves of the parse tree. And also there are some terminals that we have yet to match against. And those will all be recorded on a stack. And the important property of the stack is that the leftmost pending terminal or non-terminal is always at the top of the stack. So either the terminal we're trying to match or the non-terminal we're trying to expand will always be on top of our stack. We'll reject if we reach an error state. So if we look up one of those empty entries in the table, we will reject the string. And we'll accept if we reach the end of the input and we have an empty stack, meaning we have no pending unmatched terminals or unexpanded non-terminals. So here's the algorithm. We initialize the stack to just the start symbol S and the special symbol $. And $sign is not part of the alphabet, or you could think of it, we extend whatever our alphabet is with a new symbol called $. $sign marks the bottom of the stack, and you can think of it also as marking the end of input. So this is just a way of recording where the end of the input is going to be. Okay, so once we've matched something against S, then whatever is left had better be at the end of the input. That's what that stack expresses. And now we're in a loop, so we're going to repeat the following moves until we can't repeat them anymore, until the stack is empty. Okay, and there's two possible moves. Let's do the terminals first. So let's say the top of our stack is a terminal. So here we're dividing the stack into the top of the stack and the rest of the stack. So what are we going to do if the top of the stack is a terminal? Well, we're going to try to match the input. So we're going to say, well, at the top of the stack, the terminal on top of the stack matches the next thing in the input. Then we advance the input, and we pop the stack. So we have successfully matched the input against the terminal, and so that terminal is done, and we should progress into the stack and match the next thing that hasn't been handled yet. And if they don't match, if the terminal that we're looking at doesn't match the next thing in the input, well, that's an error. We don't have any backtracking here. There's no way to parse the string, and so we'll raise an error. Now, the second class of moves deals with the non-terminal. So let's say that the top of the stack is a non-terminal X. And remember that the top of the stack will be a non-terminal exactly when that is the leftmost non-terminal. So now what we do is we look at our parsing table under the entry for X and the next input symbol, and that should give us the right-hand side of a production. Okay? And now what we do is we pop X off the stack, and we push the children of X in the parse tree onto the stack. So this is the way we expand X. So now the leftmost unhandled thing in the parse is going to be Y1, because that's the first child of X. And then all the other children of X are next, and then whatever else is in the stack. And again, if there's no entry for the current non-terminal and input in the table, then that's an error, and the parsing stops. So let's work through an example using our parsing table. And you might want to refer back to the parsing table. I have not included it here because there isn't space for it. But I'll work through it, and you can go back and look at it at some point and convince yourself that I made the right moves. So initially, our stack is E $. So E was our start symbol, and $ is our end of input symbol. And our input, we're going to try to parse the input int times int. That's what we want to parse. And then, of course, we have our new symbol $. We'll tack that on to the end of the input. And if all goes well, the $sign on the stack will match up against the $sign at the end of the input. Again, $sign here is just a way of marking the end of the input and expressing that we need to parse the entire input. And so now, if you look up the E int entry, so the first terminal in the next terminal in the input, and the leftmost non-terminal in our parse, you will see that the action we're supposed to take is to use the production e goes to tx. And let me over here at the same time construct our parse tree. Okay, so initially our stack, again, the stack is the frontier of the parse tree. Initially, all we have is the root of the parse tree, and that is its own frontier. It's just one symbol. We haven't processed it yet. And so E is on the stack. E is unexpanded in the parse tree, and now we're going to use the production E goes to Tx. And so we'll have T and X added as children. What happens next? Well, E is popped off the stack. T and X are pushed onto the stack. And now notice, the frontier of the parse tree is Tx. These are the unprocessed leaves, either unmatched input or unexpanded non-terminals. And in fact, the stack records exactly which one is leftmost. So T is at the top of the stack, X is below it on the stack. Okay, well, we still haven't consumed any input. And now if we look at the T int entry, it says to use T goes to int Y. And so now we can expand T by int Y. And now what's going to happen is T is popped off the stack, int and Y are pushed onto the stack, and now notice the stack is int YX from top to bottom. The frontier of the parse tree is int YX. Okay? And now we have a case where we have a terminal on top of the stack, and so now we're going to try to match it against the first terminal in the input. And indeed they match, and so what happens is int is popped off the stack, and the terminal, the input pointer advances in the input. And here I've recorded that by just discarding the portion of the input that we've processed. So now we have times an int left to go, and the int has been removed from the stack. And so now what's on top of the stack is Y. Y is indeed the leftmost unprocessed thing on the frontier. And the table says that for non-terminal Y, on input times, we should use production Y goes to times T. So let's put that in here. And now what's going to happen, Y is going to be popped off the stack, times T is going to be pushed onto the stack, and now notice our stack is times T, X, and the frontier, the unprocessed frontier of the parse tree is times T, X. Okay? So now we have a terminal on top of the stack. It matches the next terminal in the input. So we pop the terminal off the stack, we advance the input pointer. Now we have T as our leftmost non-terminal. Int is the next thing in the input stream. And the table says, well, in this situation, we should use the production T goes to int Y. What does that mean? That means T gets popped off the stack, int and Y get pushed onto the stack. Notice that the stack is int YX, and the unprocessed frontier of the parse tree from left to right is int YX. Once again, we have a terminal on top of the stack. We match it against the next terminal in the input stream. They match. And now we have consumed all the input. $sign is the only thing left to go in the input, but our stack is not empty. Okay, and so at this point, what does that mean? Well, if the stack is not empty and we're out of input, then everything that's left on the stack had better generate the empty string. So we better be using only epsilon productions from here on out. And indeed, the table says that when Y is our next non-terminal and $sign, we're at the end of the input, we should use the production Y goes to epsilon. So Y goes to epsilon, that means Y just gets popped off the stack. Epsilon gets pushed on the stack. Epsilon is the empty string, so nothing gets pushed on the stack. And now we're down to X. And in the situation where X is the next non-terminal, $sign is, we're at the end of the input, so $sign is our next symbol. Then the table also says to use the production X goes to epsilon. And then what happens? Well, X gets popped off the stack and nothing gets pushed on because the production was X goes to the empty string. And now we see we have $sign on top of the stack, $sign in the input, and so we have emptied the stack, we have reached the end of the input, and so we accept. That is a successful parse. In the next few videos, we're going to talk about how to construct LL1 parsing tables. And in this particular video, we're going to begin by looking at how we build something called first sets. Before we get into the main topic of this video, which is something called first sets, we need to say a little bit about how we're going to construct parsing tables, or what the conditions are for constructing LL parsing tables. And so what we're interested in knowing, we're building a parsing table, and we want to know for a given non-terminal A, okay, this is the leftmost non-terminal, and a given input symbol, the next input symbol T, we want to know under what conditions we will make the move A goes to alpha. We'll replace A, the non-terminal, by the right-hand side alpha. All right, and that means that the entry in the AT entry in the table would be alpha. And there are two situations in which we would like to do this. All right, so the first one is if alpha can derive T in the first position. That means that beginning with alpha, there is some derivation, some sequence of moves, could be 0 or more moves, that will result in a T appearing in the first position of the string that's derived. And if there is such a derivation, then using the move A goes to alpha at this point when T is the next input symbol would be a good idea, because then we would be able to match the T. Eventually alpha could generate the T, and then we'd be able to match the T and then continue with our parsing of the rest of the input. All right, so in this situation, when alpha can generate a T in the first position, we say that T is an element of the first of alpha. T is one of the things, there may be more things, but T is at least one of the things that alpha can produce in the very first position. One of the terminals, I should say, that alpha can produce in the very first position. Now, there's another situation, a slightly more complicated situation, in which we might want to make the move, or we would want to make the move, that if we see A as the leftmost non-terminal and T is the next input, that we'd like to replace A by A goes to alpha. All right, and the situation here that we're going to consider is, what if alpha cannot derive T? So alpha cannot, in any sequence of moves, derive T. So in fact, what does that mean? That means T is not going to be in the first of alpha. Okay, so, and our next input symbol is T. We're still looking at the situation where we have A as the leftmost non-terminal and T is the next input symbol. Now, this doesn't sound very promising, because we have an input symbol T that we want to match, and the leftmost non-terminal that we've got up next, that we have to do a derivation for, can't generate the T. And so, but it turns out that it's not hopeless, that we actually may still be able to parse the string even in that situation, provided that alpha can go to epsilon. So if alpha can derive epsilon, if alpha can go away completely and we can basically erase the alpha, then it could be that some other part of the grammar can come in and match the T. All right, and so in what situation would that be? Well, here are the conditions. So if A goes to alpha as a production, and alpha can go to epsilon via 0 or more moves, all right, so alpha can eventually be completely wiped out, all right, and if T can come immediately after A in the grammar, so there has to be a derivation for this to make sense. There should be a derivation where we are using the A, okay, where the A is an important piece of the derivation, from the start symbol. And what comes immediately after the A is the next input symbol that we're expecting. So in this situation, if we could get rid of the A, then by having it go to epsilon, then we would still be on track, because potentially some other piece of the grammar could come in and match the T. All right? So in that case, we would say, what do we have to test for? Under what conditions can we do it? Well, we want to be able to do this if T can come after A in the grammar, and we say that T is in the follow of A. T is one of the things that can come after A in the grammar. Now, this is an important point and a place where people sometimes get confused, and so I want to emphasize this. Notice that we're not talking about A deriving T. Okay, A does not produce T. T appears in a derivation after A. Okay, so the A and the T here, it doesn't have anything to do with what A produces. This has to do with where A can appear in derivations. All right, so if the T can come after the A in a derivation, then we say that T is in the follow of A. All right, so in this video, we're going to focus on only this first part, the first sets. In the next video, we'll look at the follow sets, and then in the video after that, we'll talk about how to put it all together to build this parsing table. All right, let's focus now on our main topic for this video, the computation of first sets. So here, first of all, we have to have a definition of what a first set is. And so we're going to say for an arbitrary string, this is actually, X here is a string, it could be a single terminal, it could be a single non-terminal, or it could be a string of grammar symbols. All right, and if that X can derive T in the first position through some sequence of moves, then we say that T is a terminal here, is in the first of X. Okay, so all the possible terminals that can be derived in the first position will be in the first of X. Now, for technical reasons that will become clear in a minute, we also need to keep track of whether X can produce epsilon. All right, so even though epsilon is not a terminal symbol, if X can go to epsilon via 0 or more steps, then we'll say that epsilon is in the first of X. And this turns out to be needed. We need to keep track of whether whether things can produce epsilon in order to compute all the terminals that are in the first set of a given grammar symbol. All right, so now here's a sketch of the algorithm. So first of all, for any terminal symbol, well, the only thing the terminals can produce are themselves. So every terminal symbol, and here I should just say T is a terminal. So for every terminal symbol, it is in its first set just consists of the set containing only that terminal. All right, so now let's consider a non-terminal X. Okay, so here X is a non-terminal. And what are going to be the conditions when epsilon is in the first of X? Well, if there's a epsilon production, if X goes immediately to epsilon, then obviously X can produce epsilon, and epsilon should be in the first of X. But also, if X can produce any other right-hand side, all right, where everything on the right-hand side can go to epsilon, well, then the whole right-hand side can go to epsilon. So in that case, also, epsilon is in the first of X. And notice that this will only happen if it can only potentially happen if all of the AIs here are non-terminal symbols themselves. Obviously, if there's any terminal symbol on the right-hand side, then that production can never go completely to the empty string. Okay, it'll always produce at least that terminal. But if every non-terminal on the right-hand side can produce epsilon, meaning epsilon is in the first of all of those non-terminals, and there are no terminals on the right-hand side, then epsilon will be in the first of X. All right, and there's one other situation, and here's where we make use of the fact that we're keeping track of where epsilon can be produced. All right, so let's say that we have a production like this, okay, and let's say the first n symbols, A1 through AN here, can all go to epsilon. So this can all disappear, okay, and be replaced by the empty string. Well, what does that mean? So if we have a derivation like this, okay, and then through some number of moves, it goes to alpha, well, that means that X can, through a bunch of moves here, derive alpha itself. Okay, so X can go to alpha by wiping out all of the AIs, and I forgot to put the alpha here on the end. There should be an alpha after A sub n there. Okay, and what does this mean? Well, this means that anything that is in the first of alpha is going to also be in the first of X. All right, so if any prefix of the right-hand side can disappear, then the remaining suffix, the alpha, it doesn't matter what the alpha is left. Then the first of alpha will be a subset of the non-terminal on the left-hand side, X in this case. All right? Okay. All right, so that is a definition of first sets and how you compute them. Okay, and we have to compute them for the terminals and for the non-terminals. All right, that's what these second two rules here cover, the non-terminals. And just notice, as I mentioned here at the beginning, that this is well defined for any other grammar sequence as well. I mean, excuse me, any other string in the grammar as well. If I know how to compute it for terminals and I know how to compute it for non-terminals, then I can compute it for arbitrary strings in the grammar as well. All right, so now let's do an example. Let's take a look at this grammar, and let's see if we can compute the first set. So let's start with the easy stuff. Let's do the terminal symbols. All right, so for the terminals, it's really extremely straightforward. The first of plus is plus. The first of times is just times. Every terminal is has its first set. The first set of every terminal is just the set containing that terminal, and so on for the others. And this is not worth writing out. So it'll be the first of open paren will be just open paren. The first of closed paren will be just closed paren. And I think that is all. No, we have to do int as well. Okay. All right. So these are the first sets for the terminal symbols. And now let's look at something more interesting. Let's talk about the first of the non-terminal symbols. So what about the first of E? Well, if we look at the production for E, let's remember our rules. So we know that anything that's in the first of T will also be in the first of E. So the first of T is a subset of the first of E. Okay, so in order to know what the first of E is, we have to know what the first of T is. At least to know part of the first of E, we have to know the first of T. So let's move on then to first computing the first of T. Let's try to get that set. Now, the first of T is actually pretty easy because if we look at the productions for T, we can see that they produce terminals in the first position. All right, so the only possibility only possibilities in the first of T are open paren and int. And since there are only two productions for T and both of them have a terminal in the very first position, there's no other terminal symbols that could be produced in the first position by T. So we can just read off the first of T directly from the grammar. And it's the open paren and int. Okay? Now, let's return to thinking about the first of E. So remember there was another case that we have to keep track of, or that we have to consider. So it could be, so of course clearly everything in the first of T is in the first of E, all right? And we've already noted that down. But if T can go to epsilon, then things that are in the first of X could also be in the first of E. But now we've computed the first of T, and we see that epsilon is not in there. The first of T always generates at least one terminal symbol. And so there will never be a situation in which X can contribute to the first of E because T is always guaranteed to generate at least one terminal. So in fact, this subset that we wrote up here is not a subset at all, it's an equality. The first of T and the first of E are equal. So the first of E is also open paren and int. All right, so now let's take a look at the first of X. Okay, so the first of X, well, clearly plus is in the first of X because one production for X produces a plus immediately in the first position. So we can just add plus to the first of X. And then X has an epsilon production. So it can also go to epsilon, so that means that epsilon is also in the first of X. And now what about the first of Y? Well, the first of Y, it's a similar structure to the productions for plus. We see we have one production here that produces a terminal in the first position, and that's times. So the first of Y has times in it. And then Y also has an epsilon production. Y can go directly to epsilon, so epsilon is also in the first of Y. All right? And that's actually it for this grammar. These are the complete first sets for all the symbols of the grammar. The terminals just have themselves in their first sets, and then the non-terminals we computed have these sets. So that concludes our discussion of first sets. And in the next video, we're going to take a look at computing follow sets. In this video, we're going to continue our discussion of the construction of LL parsing tables by taking a look at how we build the follow sets. So here's the definition of follow of X, and recall that the follow set for a given symbol in the grammar isn't really about what that symbol can generate. It really doesn't depend necessarily at all on what the symbol can generate. It depends on where that symbol can appear, where that symbol is used in the grammar. And we say that T is in the follow of X if there is some place in the grammar, some derivation, where that terminal T can appear immediately after the symbol X. Okay, and so for all such T, they make up the follow set of X. And here's some intuition about how we would compute follow sets. Let's say we have a situation where X goes to two symbols, A, B, all right? Then anything that B can produce in the first position will clearly be in the follow of A. Clearly can follow A. So if we have x goes to AB, and then through some more steps, we can get something like this B goes to T beta, all right? Then we have a situation where the T comes immediately after the A, and so clearly something that was in the first of B is in the follow of A. So the basic rule is that if you have two symbols that are adjacent somewhere in the grammar, the first of the second one is in the follow of the first one. Okay. Now, another interesting fact here is that if we have a symbol at the end of a production, let's take a look at the B here for a moment, okay? And I claim here that anything that's in the follow of the left-hand side is going to be in the follow of B. In this case, that the follow of X is a subset of the follow of B. And let's take a look at that. Let's say that we have a situation where we have a derivation from the start symbol, okay, and we wind up with X followed by T. Okay, and there can be other stuff around the X and the T, but let's ignore that for the moment. Let's just focus on the XT. Then we can use this production, X goes to AB, and in one step, we can get to ABT. And now we see that T was in the follow of X, and also T is in the follow of B as a result. Okay, so anything that's in the follow of X will also be in the follow of B. And we can generalize this observation about what occurs at the end of a production. So anything that occurs at the end of the production, its follow set will include the follow set of this symbol on the left-hand side of the production. Well, what is the end of the production? If B can go to epsilon, if B can disappear, then A will appear at the end of the production. Okay, so if B can go to epsilon, then it would also happen that the follow of X would be in the follow of A. And following up here in our example, so we start up here, we start with the start symbol, we got to XT. In one step we got to ABT, and so T was in the follow of B. But now B can go to epsilon, and so we can also get to AT, and therefore T is also in the follow of A. And finally, there's one special case. Remember that we have our special symbol marking the end of the input, and what can that follow? Well, the end of the input is in the follow of the start symbol. All right, and this is just a way, again, of keeping track of what we're going to do when we run out of input. And we'll see how that's used when we build the parsing tables, but we always add as an initial condition that $sign is in the follow of the start symbol. So now let's take a look at and sketch of the algorithm for computing follow sets. So as we just said, the $sign is in the follow of the start symbol. And now we take a look at each production. Okay, A goes to alpha X beta, and we're focusing here on the X. Okay, so we look at every production and we look at every symbol on the right-hand side of that production. Okay, and the first of beta, okay, the thing that can follow X in this production, the first of that will be in the follow of X. And notice that we just subtract out epsilon if it was in the first of beta. We're not interested anymore in the epsilons for the purposes of follow sets. Epsilon never appears in follow sets, so follow sets are always just sets of terminals. And now, the second part of the algorithm is that if we have some suffix of a production, beta, that can go to epsilon, so epsilon is in the first of beta, all right, so this suffix of the production can completely disappear, then as we said on the previous slide, the follow of the left-hand side symbol will be in the follow of X. And that's it in terms of the rules for computing follow sets. So now let's work through an example. So here's our grammar again, and we're going to compute the follow sets for each of the symbols of the grammar. So let's begin with the start symbol. We'll start with the follow of E. And by definition, we know that dollar is in the follow of E. So we get that one easily. And now the question is, what else can be in the follow of E? All right, so in order to figure that out, we have to look at where E is used in the grammar. All right, so remember always that follow sets are about where the symbol is used, not what it produces. All right, so here is a place where E is used, and we can see that it is immediately followed by a terminal symbol, so certainly close paren is in the follow of E. All right? And there's one other place where E is used, and that's over here. And it appears at the right end of a production. And so then we know that anything that's in the follow of X is also going to be in the follow of E. And that's a constraint, and so we'll write that down over here. Okay, so this is just a property of the relationship that the follow sets will have when we're done computing them. This doesn't immediately tell us anything new that's in the follow of E, but we know that as we go along and we learn about things that are in the follow of X, we'll have to add them to the follow of E. And let me just divide up the slide here. So we'll put our properties that we know about the relationships between follow sets over on the left-hand side, and we'll put the actual follow sets over here on the right-hand side. All right, so now to make, that's the only two places, those are the only two places where E is used in the grammar, and to make further progress, we need to know something about the follow of X. Okay, if we're going to make further progress on the follow of E, we need to figure out what's in the follow of X. So let's focus on that for a minute. So where is X used in the grammar? Well, it's used in only one place, and that's here. Okay, where it appears at the right end of a production. And so therefore, the symbol on the left-hand side will be a subset of the follow set of X. So we're going to know that the follow of E is a subset of the follow of X. All right, and what does that mean? Well, so follow of X is a subset of follow of E, and follow of E is a subset of the follow of X. So that really means that these two sets are equal. Follow of X and the follow of E, whatever they wind up being, are going to have to be the same set. And now we've looked at all the places where E is used in the grammar. We've looked at all the places where X is used in the grammar. We can't learn anything more about what is in the sets, the follow sets of E and X. We're not forced to add anything else to either set. And so we're done. And so we can close off this set. And we know that the follow of E consists of $ and close paren. And we also know that X has the same set, the same follow set. All right, so now let's move on to the follow of T. All right, so what's going to be in the follow of T? Well, again, we have to look at where T is used in the grammar. So T is used in two places. The first one is here in the first production. And so what's going to be in the follow of T? Well, it could be anything that is in the first of X, okay, because X comes immediately after T. And if we recall from the previous video, there were only two things in the first of X. One was plus. So plus is definitely in the follow of T. And let's just review, excuse me, how that can happen. So we can go from E to TX, okay, using the first production. Now we see the X comes after the T. And then in one more step, we can go to T plus E. And now we have a derivation where plus follows T. And that's how that's why plus is in the follow of T. All right. So the other thing that was in the first of X was epsilon, because there's an epsilon production for X over here. But remember that we're not interested in, we don't include epsilon in follow sets. And so X doesn't contribute anything else to the follow of T. But since X can go to epsilon, remember what that means. That means that over here, looking back at this first use of T again in the grammar, this X can disappear. All right? And that means that anything that is in the follow of E is also in the follow of T. Now we already know the follow of E, so we can just add those things in, okay? And let me write that down over here just so we don't forget it. So the follow of E is a subset of the follow of T. Okay, we won't really need this fact again, but useful to write it down, perhaps. All right, and now we're done with this use of X. We've included everything implied by this production that we can in the follow of T. And so now we have to look at the other place where T is used, and that's over here, okay? And so here we're going to see that T is at the right end of a production. So anything that is in the follow of Y can also be in the follow of T. All right, so the follow of Y is going to be a subset of the follow of T. All right. So now we can go off and work on the follow of Y. We have to, in order to figure out what the follow of T is going to be, we're going to have to know the follow of Y. And so where is Y used in the grammar? Well, there's only one place, and that's over here. And notice that Y appears at the right end of a production. which means that the left-hand side symbol, its follow set, will be included in the follow of y. And so the follow of t will be a subset of the follow of y. All right, and now again, we have two follow sets that are subsets of each other. Follow of y is a subset of follow of t, and follow of t is a subset of follow of y, and so these two sets we know are going to have to be equal. Okay, so we can write down here that the follow of y includes plus, dollar, and close paren, just like the follow of t. And now we're done. We've with follow of t and follow of y, we've followed all the implications of how the follow of t gets things into what can be included in the follow of t. We looked at all the places where y is used in the grammar and added all the things that we can based on its context. And there's nothing more that we're forced to add to either set, and so we're done. Okay, we can close these sets off. They're finished. All right. So now we've done the follow of e, x, t, and y. So we've taken care of all the terminal symbols. I'm sorry, all the non-terminal symbols, but we still need to compute the follow sets for the terminal symbols. And unlike the case with first sets, the follow sets for terminal symbols can actually be interesting. So let's take a look at the follow of open paren. Okay, what can follow an open paren in a derivation? Well, open paren is only used in one place, it's here. Okay, and so what can follow an open paren is whatever is in the first of e. And remember that the first of e was the same as the first of t, because t always produces something in the first position. And the first of t was what? It was open paren and int. Okay. And if you think about this for a minute, this makes complete sense. What can come after an open paren in any valid string in this grammar? Well, it's either going to be another nested parenthesized expression, or it's going to be an integer. And in particular, you couldn't have a times or a plus immediately after an open paren, and you also couldn't have the end of the input. You couldn't have the input stop after an open paren and have a valid string. So now let's take a look at the follow of close paren. Okay, so what's in that set? Well, again, we look at where the symbol is used. It's only used here in this one production. So, and because it appears at the right end of the production, we know that whatever is in the follow of t is going to be in the follow of close paren. All right, and so what was in the follow of t? That was plus, dollar, and close paren. Okay. So now let's move on, take a look at the operators. Let's look at the follow of plus. So where is plus used? Well, it's only used here. So whatever is in the first of e is going to be in the follow of plus. And we already know what the first of e was. That was an open paren and an int. Okay. And remember also that e cannot go to epsilon. So e cannot ever disappear completely, and that's because t always produces at least one terminal. And therefore, only the things that are in the first of e are in the follow of plus. Not because e doesn't ever, because e can't go to epsilon, we only have to include the things that are in the first of e in the follow of plus. All right, and if you think about it for a minute, this makes complete sense. What can come after a plus? Well, it could be an integer. Okay, it could be the second argument to an addition, or it could be the beginning of another nested expression. And it couldn't be at times. It certainly couldn't be the end of the input, because you always have to have another argument after the plus. And I think that's it. I think that's all the other possibilities. Okay. All right. Now let's take a look at the follow of times. What can come after a times? Where is times used? It's used here. So things that are in the first of t are going to be in the follow of times again. All right, and that we already know what that is. That's the same as the first of e. That's open paren and int. And again, this makes complete sense. What can come after a times? It's either the beginning of another nested expression or an integer. It's certainly not a plus or the end of the input. Okay, and again, t cannot go to epsilon, and so that's the only thing. Those are the only things that can be in the follow of times. And then we just have one more symbol to go. We have to look at the follow of an integer, of an int. Okay, and where is that used in the grammar? Well, it's right here. All right. So what's going to be in the follow of int? Well, it's going to include everything in the first of y. Okay, and what's in the first of y? Well, times was in the first of y, and epsilon was in the first of y. But remember, we don't include epsilons in follow sets. So y contributes times to the follow of int. But now, because y can go to epsilon, there's an epsilon production for y, that means that this int could actually wind up being at the right end of this production. Okay, or it could the y could disappear, and then whatever could follow the t could also follow the int. All right, so we have to include the things in the follow of t in the follow of int. And what was in the follow of t? Well, that was a plus, it was a dollar, and it was a close paren. Okay. And what does that tell us? Well, that tells us it's okay for almost anything to follow an int, but an open paren cannot follow an int. So you can't have another nested expression begin right after an int without an intervening operator. All right, and that completes the computation of the follow sets for this example. In this video, we're going to put together what we've learned about first and follow sets to construct LL1 parsing tables. Our goal is to construct a parsing table T for a context-free grammar G. And this is done by production. So we're going to do this one production at a time. And we're going to, in turn, consider each production A goes to alpha in the grammar G. All right, so the first case is if we are trying to figure out whether we can use A goes to alpha and T happens to be in the first of alpha. All right, so if we know that some terminal T is in the first of the right-hand side, then if we were in a situation where A was the leftmost non-terminal and T was the next token of input, then expanding by A goes to alpha would be a good move because the alpha could potentially, through more productions, match the T. And so we'll add to the parsing table at the AT entry the right-hand side alpha. All right, the other situation that we're interested in is what if we need to get rid of the A? Okay, so if the A cannot possibly match the T, all right, so let's say the T is not in the first of alpha, or we have some other situation where we want to erase the A, well, then it would be okay to use production A goes to alpha, provided that alpha can actually go to epsilon, so alpha can go away completely, all right, so we can eliminate all trace of the A. And T follows A in the grammar. So T is able to come after, T is able to come after A in some derivation. So if T is in the follow of A and the right-hand side of the production can go to epsilon, then we add the move that when A is the leftmost non-terminal and T is the next input, we can expand A by A goes to alpha. And finally, a special case for dollar, because dollar is technically not a terminal symbol. If we're at the end of the input, okay, so we have some stuff left on the stack. In particular, we have the non-terminal A is still our leftmost non-terminal, but we've run out of input. Well, then our only hope is to get rid of the A completely, and so we want to pick a production for A that can go to epsilon. So we look for a production A goes to alpha where epsilon is in the first of alpha, and dollar can follow A in a derivation. So that is the procedure, or those are the rules for constructing a parsing table. And now let's work through an example. So here's our favorite grammar that we've been looking at for the last few videos. And now let's take a look at what the parsing table will look like. All right, and the parsing table will consist of columns that are labeled by the terminal symbols of the grammar. All right, so here we'll have open paren, close paren, plus, times, and int. And then the rows will be labeled by the terminal symbols. So we'll have E, T, X, and Y. All right, and now we're just going to take each production and apply our rules and see what entries in the table we create. All right, so when would we use E goes to TX? All right, well, so the first thing to observe about this production is that it cannot produce epsilon on the right-hand side. So TX always produces at least one terminal, and so the second case where we're interested in whether the production can go to zero, so it could go to epsilon, excuse me, is not going to apply. All right, so we just have to consider what it can generate in the first position. So the only things that this production can generate in the first position are things that are in the first of T, which are open paren and int. So there are two situations in which we'll use the production E goes to tx. That is if E is the leftmost non-terminal and the next input is an open paren. Okay, and the other one is that if the next input is a int. Okay, so now let's take a look at this production. All right, so when are we going to use t goes to open paren, e close paren? Well, if t is the leftmost non-terminal, all right, that's the symbol on the left-hand side, and an open paren is the next symbol in the input, okay, because that's the only thing in the first of this right-hand side, then it would be a good move to expand by open paren, e close paren. So there's only one situation where we use that production. All right, and for the other production, the other t production, we're going to use that when t is the leftmost non-terminal and there's an int in the input. So over here, we'll have int y. And I forgot one column over here for dollar. Okay, so we'll stick dollar in there at the very end. Okay, so now we've covered these first three productions. Let's take a look at this production. So when would we use x goes to plus e? Well, clearly the only thing in the first of the right-hand side is plus, and the symbol on the left-hand side is x. So the x plus entry, we would want to expand by x goes to plus e. And similarly for y, the first production involving y, when y is the non-terminal we're trying to expand and there's a times in the input, we would use the production y goes to times t. Okay, and now we just have the two epsilon productions left, and these are the only productions actually that can go to epsilon. And so when would we use x goes to epsilon or y goes to epsilon? All right, so recall that we need to know what is in the follow of x in order to know when to use x goes to epsilon. And so we computed that in the last lecture, but let's just write it down again here. Okay, and so what was in the follow of x? Well, we had to look at where x was used in the grammar. X was used there. It appears at the right-hand side of the production, so it would be things that were in the follow of e. What was in the follow of e? Well, e is the start symbol, so dollar is in the follow of e, and close paren is in the follow of e. All right? And then what was in the follow of y? That's the other one where we'll need to know the follow set. Again, we have to look at where y is used, so y is used there. That means everything that's in the follow of t is in the follow of y. The follow of y will therefore include the first of x, because x can come after t, so plus will be in the follow of y. All right, but then x can go to epsilon, and so everything that's in the follow of e will be in the follow of t, and therefore also in the follow of y. So the other two things in the follow of y were $sign and close paren. All right, and so what this is saying, okay, is that if we are in a situation where we have an x, okay, let's just focus on the x goes to epsilon production for a moment. Let's say that we have an x on the stack, okay, at the top of the stack, and dollar is our next input. Well, what can we do? We're at the end of the input, and we have to get rid of the x, so obviously we want to use the x goes to epsilon move. Okay, so that makes sense. And the other situation, the follow set tells us to use x goes to epsilon is if there's a closed paren on the stack, because the x cannot generate a closed paren by itself, but hopefully some other symbol that's on the stack will be able to generate it once we get rid of the x. Okay, so we should also use x goes to epsilon in this situation. Right? And then similarly for follow of y, or for y goes to epsilon, that production, there are three things in the follow, three terminals in the follow of y, and we should use y goes to epsilon if they are the next thing in the input. So if we see a plus and we're trying to expand to y, we'll use y goes to epsilon. If we see a closed paren and we're trying to expand to y, we'll use y goes to epsilon. And finally, if we're completely out of input and we still have a y left over, we'll use y goes to epsilon. And that is the complete parsing table. All right? And now you can see how this will work in every situation. Okay, for our leftmost non-terminal and for every possible input or lack of input, we have a production that we can use. And now there are a lot of blank entries in this table, and what do those correspond to? Let's say that we were trying to expand x, and the next input symbol was a open paren. Well, there's no entry here. Okay, and so that's an error. That's a parsing error. And so whenever you encounter a blank entry in the table, when you try to use a blank entry when you're parsing, that's going to generate a parsing error because what that tells us, the fact that there's a blank entry, it tells us that there is no valid move. There is no way that we could parse that string. And we discovered that at the point where we try to access an error or blank entry in the table. So now let's consider what happens when we try to build an LL1 parsing table for a grammar that is not LL1. And let's take a look at the simple left recursive grammar that we have looked at before. So S goes to SA is one production, and S goes to B is the other production. And to build the parser table for this, we'll need to know the first and follow sets. So let's take a look at the first of S. All right, so what can S produce in the first position? Well, it can clearly produce a B, and there's no epsilon, there's no possibility of generating epsilon from S, and so in fact that's the only thing that's going to be in the first of S. And what about the follow of S? What can follow in S? Well, it's the start symbol, so clearly dollar is in the follow of S, and then the terminal A appears right after S in the first production, and so A is also in the follow of S. And now we're ready to build our table, and it's going to be a very small table. We only have one non-terminal, and then we have two terminals, A and B, and we have the end of input symbol. So it's just 3 entries potentially in this table. All right, and so now let's take each production and see where we should put it. So let's just take a look at the second production first, because that's, well, for no particular reason. So we have S goes to B. When should we use that? Well, clearly, if we see a B in the input, this would be a good one to use because the first of the right-hand side includes B. All right, so S goes to B would be used if we see a B in the input. And now what about S goes to SA? Well, here, again, this can't generate epsilon, so we're only interested in what it can produce in the first position. And once again, the first of S is just B. And so we also have the move, in the SB entry, we would have the move S goes to SA. And now we see the problem, right? Here we have an entry that has multiple moves. This is a multiply defined entry. Okay. And what does that mean? Well, that means if we see an S if we have an S that we want to expand, okay, we're trying to, if S is our leftmost non-terminal, it's at the top of the stack, and B is our next input symbol, all right? This table doesn't tell us exactly what move to make. It's not deterministic. It says there's 2 possible moves that we can make. And so this is how you know a grammar is not LL1, because if it winds up that you build the LL1 parsing table and then you have more than one entry, more than one possible move in some position in the table, some entry, excuse me, I used the word entry incorrectly. So if you wind up, let me say that again. If you build the table and some entry in the table has more than one move in it, then there's not a unique move for every situation for the parser, and that grammar is not LL1. So as we just said, if any entry is multiply defined in the parsing table, then the grammar is not LL1. And in fact, this is the definition of an LL1 grammar. So the only way to be sure that a grammar is LL1, or the mechanical way to check that a grammar is LL1, is to build the LL1 parsing table and see if all the entries in the table are unique. Now, that we do know, however, that there are certain classes of grammars that are guaranteed not to be LL1, not to be LL1. And what are some of those? Well, any grammar that is not left factored will not be LL1. Okay. Any grammar that is left recursive will not be LL1. Okay. And any grammar that is ambiguous is also guaranteed to not be LL1. But this is not an exhaustive list. Other grammars are not LL1 too. So in particular, if a grammar required more than one token of look ahead, it would not be LL1. But even that isn't a complete list. There are even grammars beyond that that are not going to be LL1. So what this amounts to, these 3 things here amount to quick checks that you can do to test whether a grammar is guaranteed not to be LL1. But if just because a grammar is left factored and it is not left recursive and it is unambiguous that doesn't guarantee that it's LL1. And the only way to know for sure is to construct the parsing table and see if all of the entries in it are unique. And unfortunately, it turns out that most programming languages, their context-free grammars, or the grammars that describe most programming languages, are not LL1. And the LL1 grammars are too weak to actually capture all of the interesting and important constructs in commonly used programming languages. And there are more powerful formalisms for describing grammars and or practical grammars, and we're going to be looking at those in future videos. It turns out that they build on everything that we've learned here over the last few videos for LL1 grammars, so none of that will be wasted, but they assemble those ideas in a more sophisticated way to build more powerful parsers. This is the first of what will be a considerable sequence of videos on bottom-up parsing. The first thing to know is that bottom-up parsing is more general than deterministic top-down parsing. So recall we talked about recursive descent, which is a completely general parsing algorithm but requires backtracking. And now we're focused on deterministic techniques, and we talked about LL1 or predictive parsing last time, and now we're going to shift gears and talk about bottom-up parsing. And it turns out that even though bottom-up parsing is more general, it's just as efficient, and it uses all of the ideas that we learned in top-down parsing. And in fact, bottom-up parsing is the preferred method that's used in most of the parser generator tools. So one good thing about bottom-up parsers is they don't need left-factored grammars, so we can revert to the natural grammar for our example, and natural here is in quotes because we still have to encode the precedence of plus and times. So bottom-up parsers aren't going to deal with ambiguous grammars. And let's just, as an example, consider how a bottom-up parser would work on the following typical input string. So the first thing to know about bottom-up parsing is that it reduces, what we call reduces a string to the start symbol by inverting productions, by running productions backwards. So here's an example. On the left-hand side is the sequence of states of the string, and on the right-hand side are the productions that were used. And the thing to observe, let's just look at the very first step, is that we began with the entire string. We began with the string of terminals, and we picked some of those terminals, in this case just one, this particular int right here, and we ran a production backwards. We replaced the int here by the left side of the production. We matched the right side of the production int, and we replaced it by the left side. So int went backwards here to t. And then in the next step, we took int times t, this substring of the string that we're working on, and we replaced it by the left-hand side of this production. Int times t was replaced by t. And so on. At each step here, we're matching some portion of the string, and I'm underlining the portion that's being replaced at each step. And we're running, and that matches the right-hand side of some production, and then we're replacing that substring by the left-hand side. And finally, this entire string here is replaced by e. And we wind up at the start symbol. So we began with an input string. This is our input string up here, our input string of tokens. And we end with the start symbol down here. And if you read the moves in this direction, if you start at the bottom and read towards the top, well, these are just productions. And in fact, this whole thing is a derivation. This is just a normal derivation going from bottom to top. But in this direction, when we run it backwards, beginning with the string towards the start symbol, we call these reductions. And I haven't told you exactly how we decided what reductions to do, and you might wonder, well, how did I know to do this particular sequence of reductions? Well, here's another interesting property of bottom-up parsing. So if you read the productions backwards, they trace a rightmost derivation. So if we begin here with E, so remember, the parser is actually going in this direction. So this is the direction of parsing here. But now we're going to look at the steps the parser took in reverse, and we're going to see that it was, in fact, a rightmost derivation. So here E went to t plus E. Well, E was the only non-terminal. But then E here is the one that's expanded. It's the rightmost non-terminal. And then this t is expanded. It's also the rightmost non-terminal to get int. And now this t is the rightmost non-terminal. It's expanded to get int times t. And then this is the only and rightmost non-terminal. And so we wind up with the whole input string int times int plus int. And this leads us to the first important fact about bottom-up parsing, which is that a bottom-up parser traces a rightmost derivation in reverse. All right, so if you're ever having trouble with bottom-up parsing, it's always helpful to go back to this basic fact. A bottom-up parser traces a rightmost derivation, but it does so in reverse by using reductions instead of productions. So here's the series of reductions again shown on the left, and here is the parse tree that's constructed from those reductions. And this is actually, I think, a very helpful picture if we animate it to see the sequence of steps and to see what a bottom-up parser is really doing. So here we begin with the input string over here, and we show the same input string here. And now we're going to just walk through the sequence of steps that the bottom-up parser takes, a series of reductions, and show how it builds an entire parse tree. And the basic idea is that at each step we're performing a reduction. And remember, when we do a reduction, we replace the children of the right-hand side of some production by its left-hand side. And just like when we were doing top-down parsing, we would make the right-hand side the children of the left-hand side. Well, we'll do the same thing here. So here's the child in the input, and then we make t its parent. And now you can see what's going to happen. A top-down parser begins with the start symbol and produces the tree incrementally by expanding some non-terminal at the frontier, at a current leaf of the partially constructed parse tree. The bottom-up parser is going to begin with all the leaves of the eventual parse tree, the entire input, and it's going to build little trees on top of those. And it's going to be pasting together all of the subtrees that it's put together so far to build the complete tree. Let's walk a few more steps and see how that happens. So in the next step, we go from int times t to t, and so int times and the subtree rooted at the other t become children of this non-terminal t. And you can see we've taken these three subtrees here and pasted them together into a larger tree. So as we go through the parse, bigger and bigger portions of the original input are going to be pasted together into larger and larger trees. And the next reduction takes the int at the far end of the input and reduces it to t. And that gets reduced to e. And then at the very end, the three remaining subtrees are all pasted together into one parse tree for the whole thing with the start symbol as the root. So to summarize, a bottom-up parser traces out a rightmost derivation in reverse, and it builds a parse tree by combining small parse trees into larger ones. It proceeds bottom-up. Instead of expanding out from the start symbol top-down, it builds from the leaves of the tree up towards the root. In this video, we're going to continue our discussion of bottom-up parsing with the main strategy used by all bottom-up parsers, so-called shift-reduce parsing. Here's a quick review of the most important thing that we learned last time, that a bottom-up parser traces a rightmost derivation in reverse. Now, this particular fact has an important consequence. So let's think about a state of a shift-reduce parse where we have some strings alpha, beta, and omega. And let's assume that the next reduction is going to be to replace beta by x. Okay, so remember we're running productions backwards. Then I claim that omega has to be a string of terminals. And why is that? Well, if you think about it, if this is a rightmost derivation in reverse, then when x is replaced, when we take this, if we look at the forward step instead of the backward step, so remember the parser is running this way, replacing beta by x, but if we think about the rightmost derivation in the other direction, then x has to be the rightmost non-terminal, which means there are no non-terminals to the right of x. And so all the characters, all the tokens or whatever it is in this string have to be terminal symbols. Now it turns out that those terminal symbols to the right of the rightmost non-terminal are exactly the unexamined input in bottom-up parser implementations. That is, if I have alpha x omega and and X is my rightmost non-terminal, then this is the input that we haven't read yet. This is unexamined input. And it's going to be useful to mark where we are in the parse, where our input focus is. And we're going to do that by using a vertical bar. So we're going to just drop a vertical bar between the place where we've read everything to the left, and we've actually been working on this. So this stuff to the left here can be terminals and non-terminals, and the parser has seen all of that stuff. And the stuff to the right is stuff that the parser hasn't seen yet. We don't know what's out there, although we do know it's all terminal symbols. And the vertical bar is just going to mark the dividing line between the two substrings. To implement bottom-up parsing, it turns out we only need two kinds of actions, shift moves and reduce moves. And we've already talked somewhat about reduce moves, and so we have to introduce shift moves. So let's do that now. So a shift move reads one token of input, and we can explain that or represent that by moving the vertical bar one token to the right. So if our input focus is here and we want to read one more token of input, then we just move the vertical bar over, and this signifies that now the parser knows about that next terminal symbol, and now it can start working on it. It can do things with it and match against it for the purposes of performing reductions. Again, the stuff out here to the right of the vertical bar the parser hasn't seen yet. And then a reduce move is to apply an inverse production at the right end of the left-hand string. So if we have a production, A goes to XY, and we have X and Y here immediately to the left of the vertical bar. So this is our focus point. Okay, and X and Y, the right-hand side of the production is right there. Then we can do a reduction. We can replace that right-hand side by the left-hand side. And this is a reduce move. Here is the example from the last video, and this is exactly the example, just showing the reduce moves, now with the vertical bar also shown. So this shows where the input focus was at the point where each of the reductions was performed. And what's missing, of course, now we know, is the sequence of shift moves. So here is the sequence of shift moves and reduce moves that take the initial input string to the start symbol. So let's walk through this in more detail. So we're going to go step by step, and we're going to show each shift and each reduce move. And now, in addition to our input string down here, we also have a pointer showing where in the input we are. So initially we haven't seen any of the input, and our input pointer is to the left of the entire string. So the first move is to do a shift. And then we do another shift, and then we do another shift. And now, just looking at the example from before, if you look back at that example, you know the next thing we need to do is a reduce. And remember, we're only allowed to reduce to the left of the arrow. So we can only reduce over on this side of the arrow. So we always have to have read enough of the input before we can perform a reduce move. And then we perform another reduce move. Okay. And then it turns out the next thing to do is two shift moves, and we haven't explained yet how we know whether to shift or reduce. We're going to get there. I'm just showing that there exists a sequence of shift and reduce moves that succeed in parsing this example. Now we've shifted the entire input onto this. We've shifted over the entire input, so there's no more input to read, and now all we can do is reduce moves. But fortunately, there is a sequence of reduce moves from this point that we can perform. So here we reduce int, and then we reduce t plus t. Oh, forgot. We first reduce t to e, and then we reduce t plus e back to the start symbol. It turns out that this left string, the stuff to the left of the vertical bar, can be implemented by a stack. And that's because we only do reduce operations immediately to the left of the vertical bar. So it's always some suffix of the string to the left of the vertical bar where the reduction is happening. So what a shift move then does is to push a terminal onto the stack. It reads one token of input and pushes it on the stack. And then a reduce pops some number of symbols off of the stack. That's the production right-hand side. And then it pushes one non-terminal onto the stack. That's the production left-hand side. Now it can happen that in a given state that more than one action, shift or reduce, may lead to a valid parse. So in particular, if it's legal to shift or reduce, if you could do either one of those things, then we say there is a shift-reduce conflict. The parser could either read one token of input and push it on the stack, or it could perform a reduction. If it's legal to reduce by two different productions, then there is what is called a reduce-reduce conflict. Okay, so reduce-reduce conflicts are always bad, or almost always bad. They indicate usually some kind of serious problem with the grammar. Shift-reduce conflicts are not good, but they're often easier to remove. So if you have reduce-reduce conflicts, particularly when you're building your grammar for cool, then you're doing something seriously wrong. If you have shift-reduce conflicts, then that's almost to be expected because you're probably going to need to use precedence declarations to remove them, and we'll talk about that some more in another video. But in general, if you have either one of these conflicts, it means that there's some state in which the parser doesn't know what to do, and you either need to rewrite the grammar or give it a hint as to what it should do in order to successfully parse your language.